Welcome! Today, we will explore LeetCode problem number 1806, titled Minimum Number of Operations to Reinitialize a Permutation. In this problem, we aim to determine the minimum number of operations required to restore a permutation to its original state. Stay tuned as we dive into the problem, explore the logic, and break down the solution in an easy-to-understand way. Let's get started. In this problem, we are working with a permutation of integers from 0 to n1, where n is guaranteed to be an even number. A permutation simply means a specific arrangement of these integers. Initially, the permutation is given as perm equals 0, 1, 2, and 1. Now, the task involves performing a specific operation repeatedly. In each operation, we construct a new array ARR of the same length. For every index I, if I is even, the value at ARR, I, is set to the value at perm, I/2. On the other hand, if I is odd, ARR, I, is set to the value at perm, n/2 plus, I1/2. After constructing ARR, we replace the current permutation perm with ARR. The goal is to determine the minimum number of these operations required to return the permutation back to its original order of 0, 1, 2, and 1. The output of the problem is an integer, which represents the minimum number of operations needed to restore the original permutation. Let's look at a few examples to better understand this. In the first example, we have n equals 2. Initially, perm equals 0, 1. If we perform the operation, for I equals 0, the value at ARR, 0, becomes perm, 0, which is 0. For I equals 1, the value at ARR, 1, becomes perm, 1, which is 1. After completing the operation, ARR is 0, 1, which matches the original permutation. Since only one operation was needed to restore the permutation, the output is 1. In the second example, we are given n equals 4 and the initial permutation is perm equals 0, 1, 2, 3. Performing the first operation, for I equals 0, ARR, 0, becomes perm, 0, which is 0. For I equals 1, ARR, 1, becomes perm, 2, which is 2. For I equals 2, ARR, 2, becomes perm, 1, which is 1. Finally, for I equals 3, ARR, 3, becomes perm, 3, which is 3. After this operation, ARR is 0, 2, 1, 3. This does not yet match the original permutation, so we perform a second operation. Starting again, for I equals 0, ARR, 0, becomes perm, 0, which is 0. For I equals 1, ARR, 1, becomes perm, 2, which is 1. For I equals 2, ARR, 2, becomes perm, 1, which is 2. For I equals 3, ARR, 3, becomes perm, 3, which is 3. After completing this second operation, ARR becomes 0, 1, 2, 3, which matches the original permutation. Therefore, the minimum number of operations required to restore the permutation is 2. In another example, for n equals 6, the initial permutation is 0, 1, 2, 3, 4, 5. In this case, it takes a total of 4 operations to reinitialize the permutation back to its original state. Finally, let's discuss the constraints and edge cases for this problem. The value of n is always an even integer and lies between 2 and 10,000. For the smallest case of n equals 2, the output is always 1, as the permutation reinitializes in just one operation. For larger values of n, the number of operations required increases, but the algorithm must still compute the result efficiently, even for the maximum constraint of n equals 10,000. Additionally, the even nature of n ensures that calculations involving even and odd indices are well defined. These constraints and edge cases help ensure that our solution is both robust and efficient across all possible inputs. To solve the problem of determining the minimum number of operations to reinitialize a permutation, we need to understand how the transformation works. The permutation starts as 0, 1, 2, and 1, and a specific transformation is applied repeatedly. If the index I is even, the new value at I is taken from perm, I/2. If I is odd, the new value at I is taken from perm, n/2 plus, I1/2. Our goal is to calculate how many times this transformation needs to be applied before the permutation returns to its original order. To tackle this problem, we will explore multiple approaches to identify the most efficient solution. The brute force approach is the most straightforward way to solve the problem. Here, we simply simulate the transformation process step by step. We start with the original permutation 0, 1, 2, and 1 and apply the transformation rules to generate the next permutation. Each time we apply the transformation, we increment a counter to track the number of operations. This process is repeated until the permutation matches its original order. While this approach is simple and easy to implement, it has significant drawbacks in terms of efficiency. Each transformation takes O(n) time, and in the worst case, we may need to perform up to O(n) operations, leading to an overall time complexity of O(n) squared. Additionally, it requires O(n) space to store the intermediate permutations. For larger values of n, this approach becomes impractical. A more efficient solution is based on the observation that the transformation defines cycles for the indices of the permutation. Instead of simulating the entire array, we can track the cycle length of a single index. For example, if we start with I equals 1, we can repeatedly apply the transformation rules to determine the new position of this index. The number of transformations required for the index to return to its original position gives us the cycle length, which is also the minimum number of operations needed to reinitialize the permutation. This works because all indices in the permutation share the same cycle length due to the even value of n. This optimized approach reduces the time complexity to O(n), as we only track one cycle, and the space complexity to O(1), since no additional storage is needed. By focusing on the deterministic mapping of indices, we eliminate the inefficiencies of the brute force method. The optimized approach of tracking the cycle length of a single index is the most efficient solution for this problem. While the brute force method is helpful for understanding the mechanics of the transformation, it is computationally expensive and impractical for larger values of n. In contrast, the optimized approach leverages the deterministic nature of the transformation to minimize both time and space complexity. With a time complexity of O(n) and constant space usage, it scales well and is suitable for all valid input sizes. This approach highlights the importance of recognizing patterns and properties in the problem, such as the uniform cycle length for all indices, which allows us to simplify the solution significantly. By carefully analyzing the problem, we arrive at a clean and efficient strategy to determine the minimum number of operations required to reinitialize the permutation. This problem challenges us to determine the minimum number of operations required to reinitialize a permutation back to its original order. The permutation, perm, is of size n, where n is always even. A transformation function is defined such that for an even index I, the new value at arr I is taken from perm I/2. For an odd index I, the value is taken from the second half of the array at position n/2 plus I1/2. Our goal is to repeatedly apply this transformation and count how many iterations are needed until the permutation returns to its original state of 0, 1, 2, and 1. To solve this, we start by initializing the original permutation perm and use a variable step to track the number of transformations. We also maintain a helper array, cur, to store the updated permutation after each transformation, which initially matches perm. The next step involves iteratively applying the transformation until the permutation returns to its original state. In each iteration, we increment the step counter to track the number of transformations that have occurred. For every index I in the array, we calculate the updated value for the transformation. If the index I is even, the new value is taken from perm I/2. If the index is odd, the value is derived from perm n/2 plus I1/2. After updating all the values, the perm array is replaced with the transformed cur. At the end of each step, we compare cur with the original permutation. If they match, the loop terminates. Finally, the algorithm outputs the step count, which represents the minimum number of transformations required to return to the original order. To better understand the algorithm, let's explore some key insights. The transformation alternates between reorganizing even and odd indices, creating a cyclic pattern. This cyclic behavior ensures that, after a certain number of transformations, the permutation will inevitably return to its original order. The task, therefore, boils down to finding the cycle length of this permutation pattern, which directly corresponds to the minimum number of steps needed. Additionally, the problem allows us to leverage the mathematical structure of the transformation to optimize the solution, helping us avoid unnecessary computations when dealing with large input sizes. There are several optimizations that can make this algorithm more efficient. First, by observing the pattern of even and odd transformations, we can use modular arithmetic to track the movement of indices without explicitly constructing the entire array. This eliminates the overhead of repeatedly updating the array. Furthermore, by focusing on the movement of indices rather than simulating the full transformation, we can save both time and space. The key data structures include an array to store the permutation's current state and integer variables to track the number of steps and efficiently compute index positions. In terms of complexity, each transformation takes n time as we iterate through all indices. The total time complexity depends on the cycle length, resulting in k*n, where k is the number of transformations. Space complexity is n, as we maintain a single array for the current state. Finally, it's important to account for edge cases. For small values of n, such as n equals 2, the permutation quickly returns to its original state in just one step. For larger values of n, the algorithm must handle the increased complexity efficiently by avoiding redundant calculations. Additionally, since the problem assumes n is even, the algorithm should validate the input to ensure this constraint is met. Proper handling of these edge cases ensures the solution remains robust and performs well across all valid inputs. This Python implementation solves LeetCode problem number 1806, minimum number of operations to reinitialize a permutation. The solution is based on simulating the transformation process and counting the number of operations required to return the permutation to its original state. We start by defining the function Reinitialize permutation, which takes the integer n, the size of the permutation, as input. The initial permutation is represented as a list ranging from 0 to n1, and we store this as both perm, current state, and original, to compare against. The algorithm proceeds with a while loop that continues until the current permutation matches the original. Inside the loop, the transformation rule is applied using a list comprehension. For each index I in the range of n, if I is even, the new value at I is perm, I/2. If I is odd, the new value at I is perm, n/2 plus, I1/2. After applying this transformation, the operation count is increment. If the transformed perm matches the original permutation, the loop breaks, and the function returns the total number of operations. This approach ensures correctness by directly simulating the process step by step. The time complexity is n*k, where k is the number of operations until the original state is reached. The space complexity is n, due to the storage of the permutation list. This solution is efficient for the given constraints and provides an accurate result for any even-sized permutation. Here, we start by defining a class called solution and implementing the method Reinitialize permutation. This method takes an integer n as input, representing the size of the permutation array. First, we create the permutation array perm, which is initialized to contain values from 0 to n1 in sequential order. We also clone this original array into a new array called original, so we can later compare it to the transformed states. Next, we initialize a variable operations to 0, which will track the number of transformations needed to return the permutation to its original state. Inside a while loop, the transformation process begins. We allocate a new array, newPerm, which will store the updated permutation after each operation. For each index I in the array, we determine its new value. If I is even, the value at index I is taken from the first half of the perm array, otherwise, it comes from the second half. This implements the transformation logic as described in the problem statement. Once the transformation is complete for all indices, we update perm to reference new perm and increment the operations counter. Now, after updating the perm array, we check if it matches the original array. To do this, we call the helper method isEqual, which ensures that every element of the two arrays is identical. If perm matches the original state, the transformation process is complete, and we exit the loop. Otherwise, the loop continues, performing additional transformations. Finally, we return the operations counter, which gives the minimum number of operations required to reinitialize the permutation. The isEqual method itself is straightforward. It first checks if the lengths of the two arrays are the same. If not, it immediately returns false. Otherwise, it iterates through each index and compares corresponding elements of the two arrays. If any mismatch is found, it returns false, otherwise, it returns true after completing the comparison. This helper method ensures the correctness of our logic by verifying when the permutation has returned to its original state. To solve this problem, we need to determine the minimum number of operations required to return a permutation back to its original order. Let's start with an example where n is 4. First, we initialize the permutation, perm, as 0, 1, 2, 3, which represents the original order. We also store this original order in a separate array called original and set a counter, operations, to 0. Now, for the first operation, we apply the given transformation rules. When I is even, perm, I, is updated to perm, I //2, and when I is odd, perm, I, is updated to perm, n//2 plus, I1, //2. Applying this transformation, the updated perm becomes 0, 2, 1, 3. With this, the operations counter is increment to 1. Next, we perform the transformation a second time. Using the same rules, we compute the new perm as 0, 1, 2, 3. At this point, we observe that perm matches the original array, indicating that the permutation has returned to its initial state. Therefore, we stop here and conclude that the minimum number of operations required in this case is 2. This gives a final output of operations equals 2. Now, let's consider another example where n equals 6. We start by initializing perm and original as 0, 1, 2, 3, 4, 5, and the operations counter is set to 0. For the first operation, applying the transformation results in the new perm being 0, 3, 1, 4, 2, 5, and we increment operations to 1. For the second operation in this example, applying the transformation updates perm to 0, 4, 3, 2, 1, 5, and the operations counter becomes 2. Then, for the third operation, the transformation is conducted once again, and the new perm is 0, 1, 2, 3, 4, 5. At this stage, perm matches the original array, so we stop. The minimum number of operations required for n equals 6 is therefore 3, and the final output is operations equals 3. Finally, let's explore a larger example with n equals 8. We begin by initializing perm and original as 0, 1, 2, 3, 4, 5, 6, 7, and the operations counter is initially 0. In the first operation for n equals 8, applying the transformation results in perm becoming 0, 4, 1, 5, 2, 6, 3, 7, and we increment operations to 1. Next, during the second operation, the transformation updates perm to 0, 2, 4, 6, 1, 3, 5, 7, and the operations counter increases to 2. Finally, in the third operation, the transformation brings perm back to 0, 1, 2, 3, 4, 5, 6, 7. At this point, perm matches the original array, so we stop. For n equals 8, the minimum number of operations required is 3, resulting in a final output of operations equals 3. The time complexity of this problem revolves around analyzing the number of operations needed to revert the permutation to its original state. First, we focus on the transformation of the perm array. Each operation applies a rule where the array is rebuilt according to specific indexing logic. This involves iterating through all n elements, with each access and assignment taking constant time. As a result, constructing the new array takes n time. Additionally, after every transformation, the algorithm checks whether the current perm matches the original array. This comparison involves iterating through both arrays, which also requires n time. Finally, the number of iterations depends on how the transformation cycles through all possible states of the permutation. While this count depends on the structure of the permutation, it is bounded by the size of the array, n. For powers of 2, this upper bound is further reduced due to the cyclical nature of the transformation, which we will discuss next. For arrays where n is a power of 2, the transformation organizes indices in a manner that resembles bit manipulation. This pattern guarantees that the permutation cycles back to its original state in at most log n steps. Combining this with the work done in each iteration, we see that each operation, comprising the transformation and the equality check, takes O(n) time. Since the loop executes for at most O log n iterations, the total time complexity becomes O(n * log n. Now turning to space complexity, we observe that the perm array, which holds the current state of the permutation, occupies O(n) space. Similarly, the original array, which stores the initial state, also requires O(n) space. Additionally, the intermediate storage used during the transformation, such as in the list comprehension, temporarily holds O(n) elements as well. These are the primary contributors to space usage. No additional memory beyond these arrays is required, so the total space complexity is O(n). Comparing this approach with a brute force method, we notice some key differences. A naive solution would repeatedly transform the permutation and perform checks without accounting for the predictable structure of the transformation. While the asymptotic time complexity of such a method would also be O(n * log n, it would likely involve more redundant computations, making it less efficient in practice. The optimized approach we are using directly leverages the cyclical behavior seen in cases where n is a power of 2, minimizing unnecessary operations. In terms of best, average, and worst-case scenarios, the best case occurs when the permutation reinitializes after the first transformation, which is only possible for trivial cases like n equals 2, where the time complexity is O(n). For larger values of n, including powers of 2, the time complexity remains O(n * log n, due to the logarithmic number of iterations. The reason this logarithmic behavior arises lies in the mathematical properties of the transformation rule. Specifically, when n equals 2 raised to the power of k, the transformation essentially reorganizes indices such that they return to their original positions within at most k steps, where k is logarithmic in n. Each of these steps requires O(n) work for the transformation and comparison, leading to a total time complexity of O(n * log n. This analysis highlights how the predictable structure of the permutation allows us to efficiently solve the problem, avoiding unnecessary computations and ensuring the solution is both time and space efficient. When working on this problem, one common mistake is misunderstanding the rules for reinitializing the permutation. Remember, for even indices, the transformation rule is ARR I equals perm I // 2, and for odd indices, it's ARR I equals perm n // 2 plus I'd 1 // 2. Misinterpreting these rules will lead to incorrect computations and can completely throw off the process of identifying the permutation cycle. Another frequent mistake is incorrectly assuming that the cycle length is always equal to n. This isn't true. The cycle length can be much smaller than n, and failing to verify this can result in wasted computation. Lastly, skipping edge cases, particularly for small values of n like n equals 2 or n equals 4, is another pitfall. These smaller cases often highlight unique behaviors or can help debug issues in your implementation, so it's important to account for them in your testing process. Another major issue is relying on brute force without optimization. Directly simulating the permutation repeatedly might seem straightforward, but it leads to inefficient solutions with a time complexity of O(n²) for larger n. Instead, identifying the cycle length allows you to optimize this to O(n). Additionally, assuming that the input permutation always starts as 0, 1, in 1 is problematic. The problem explicitly states that perm may require reinitialization, so skipping this verification step violates the constraints and can result in incorrect solutions. Always ensure that your implementation checks the initial state of perm before proceeding. To perform well in interviews, focus on the core concept of cycle detection. This problem is fundamentally about finding the smallest cycle that restores the original permutation, so identifying and calculating the cycle length efficiently is key. Using modulo arithmetic to track indices during the transformation can further optimize your approach. Pay close attention to the constraints of the problem, like the guarantee that n is even, as this simplifies the analysis and demonstrates your understanding of the problem space. You can also relate this to graph theory by framing the permutation process as a directed graph and finding the cycle length. Finally, if you choose to start with a brute force solution, make sure to explain its limitations and how you plan to optimize it using cycle detection. This shows a clear thought process and understanding of trade-offs. There are several related problems that can help deepen your understanding of this topic. For example, LeetCode number 202, happy number, involves cycle detection in number sequences, while LeetCode number 142, linked list cycle 2, focuses on detecting cycles in linked structures. LeetCode number 31, next permutation, deals with permutations in their order, and LeetCode number 136, single number, highlights pattern recognition in arrays. In terms of alternative approaches, brute force simulation involves iterating through the transformation repeatedly until the original permutation is restored. While this is easy to implement, it's inefficient for large N. A more efficient approach is cycle detection using fast and slow pointers, similar to Floyd's algorithm for linked lists, which allows you to detect cycles with better performance. For those with a strong mathematical background, deriving a formula for the cycle length based on the transformation rules can be the fastest method, though it requires a deeper analytical insight. Each approach has its trade-offs, so choose one that best fits the situation and your expertise. Great job! To summarize, we tackled the problem minimum number of operations to reinitialize a permutation, focusing on cycle detection and simulation. Remember, understanding permutations and their properties is key to solving similar problems. Thanks for watching, and be sure to like, subscribe, and share for more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!